All right, today we're looking at a brand new material that could completely change everything from the battery in your phone to the future of electronics. It's called goldine, and it's a revolution that's happening at the atomic scale. But let's start with a problem that I'm sure you know all too well. You know that feeling, right? Your phone's about to die, your laptop's flashing that low battery warning, and you're just wishing that our battery tech could finally catch up with the rest of our world. It's a feeling we all have, and it's a huge problem scientists have been trying to crack for decades.
So, to get that huge leap forward in battery power, researchers have been looking really closely at a technology called lithium sulfur. On paper, this thing is a dream come true for storing energy. I mean, it promises to hold way more power, be better for the environment, and use materials that are super cheap and easy to find. But, and this is a big but, there's a massive gap between that dream and the reality. When you actually build one of these batteries, they fail. And they fail fast. The capacity just tanks, they're super inefficient, and they're just not stable enough to actually use. That dream battery, it becomes a total dud. And it all boils down to one single, really destructive chemical problem. It's called the polysulfide shuttle effect. Now, that sounds complicated, but just think of it like an internal leak. These really important molecules, the lithium polysulfides, are supposed to stay on one side of the battery. But instead, they dissolve and just start wandering over to the other side. This shuttle basically short-circuits the battery from the inside, just draining its energy and absolutely killing its lifespan.
So how on earth do you plug a leak that's happening at the molecular level? Well, to solve this, scientists turn to this incredible new world of two-dimensional materials. We're talking about materials that are engineered to be just a few atoms, or in some cases, a single atom thick. The hope was that one of these super-thin sheets could act like a barrier, or maybe even a trap, to stop those leaky polysulfides. So what's so special about going 2D? Well, at this ridiculously small scale, the properties of materials just change completely. They have these huge surface areas, you can actually tune their electronic structure, and they can be incredibly reactive. They are, the perfect candidates to try and build some kind of molecular trap. Now, the most famous 2D material, of course, is graphene. It's superconductive, it's incredibly strong, it seemed like a perfect fit, but it had one fatal flaw. See, graphene is nonpolar, which means it doesn't have the right kind of electrical charge to get a chemical grip on things. So those polysulfides, they just slipped right past it. The leak wasn't plugged, and the problem was still there.
So, if the materials we already have won't work, what do you do? Well, scientists realized they had to create something completely new. And this is where a team at Linköping University in Sweden did something historic. Something that honestly sounds like it came straight out of science fiction. They created goldine, and it is no joke, exactly what it sounds like. A freestanding sheet of gold that is only one single atom thick. Just try to picture that. Taking a piece of gold foil and making it thinner and thinner until it's literally as thin as it can possibly be. I mean, this is a massive achievement. As the university itself said, this is the very first time anyone, anywhere, has managed to do this. And by making gold two-dimensional, they unlocked totally new properties that just don't exist in the regular gold that we see in jewelry.
And a breakthrough like this doesn't just happen by accident. It's the result of years and years of work at the Materials Laboratory in Linköping, or MAL. This is exactly the kind of thing that happens when you bring brilliant people together to solve real problems, literally one atom at a time.
So this is fantastic science. But let's get back to our battery. The real question is, how does a sheet of gold that's only one atom thick actually solve that destructive polysulfide shuttle problem?
Well, it turns out goldine is the perfect molecular trap. Its unique 2D structure creates this really powerful chemical bond with those leaky lithium polysulfides. It doesn't just block them, it anchors them. It grabs onto them and just stops them from migrating across the battery. The shuttle effect is stopped dead in its tracks.
And the theoretical studies give us the hard data to prove exactly why it works so well. Okay, this number, 0.47 electron volts. It might not mean much to you or me, but in the world of chemistry, that is an incredibly low amount of energy needed to make a reaction happen. It means the whole process is super efficient and happens almost effortlessly.
And we can see just how strong that chemical grip is right here. This is what scientists call adsorption energy. So those problem molecules, the Li-S clusters, they bind to goldine with a really strong energy. But pure sulfur, which you want to leave alone, it barely interacts at all. It's like goldine is selectively grabbing only the troublemakers. It's an incredibly effective trap.
But here's the really cool part. Goldine doesn't just trap these molecules, it's also an active catalyst.
It grabs the polysulfides and then helps convert them into their final, stable form. So it's not just a goalie, it's actively helping the whole reaction happen correctly, making the entire battery chemistry work the way it's supposed to.
So solving this battery problem is obviously a massive deal. But the potential for GoldNeat goes so much further. We are literally talking about the birth of a brand new class of material.
I mean, think about it. Because it's a metal that's only 1 atom thick, it has incredible properties. We're talking graphene-like conductivity, but it's also flexible and it resists corrosion. This could mean we use way less gold in our electronics, we could make ultra-fine circuits, or even build electronics that can stretch. It just opens up a whole new playbook for engineers.
You know, the creation of Goldene is just a powerful reminder that we're really only scratching the surface of what's possible. It proves that materials we've known about for thousands of years, like gold, can still hold incredible secrets. And it leaves you with a pretty fascinating question, right? What other impossible materials are out there just waiting to be discovered? And what kind of futures are they going to unlock for all of us?